I'll put this into full screen mode. Okay, so we were discussing about the WRF model physics yesterday, and as I said earlier, that WRF model is like a full-fledged three-dimensional numerical laboratory for the atmosphere. Here you find everything that you have studied so far in the MSc Atmospheric Science. Okay, it has got dynamics in it, it has got physics in it, it has got all kinds of parameterizations, visitations, land surface processes, clouds, topography, everything. Okay. So one by one we shall try to discuss briefly. Of course, all these things you have also studied already now in the NWP course. And as I mentioned yesterday, in this WRF physics, I found there were 133 slides, and it's too many slides, of course, to complete in 1 hour. So, but I want to finish this quickly. Hopefully, I want to finish this WRF model part by this weekend, possible. And so I will be just quickly flashing the slides, maybe explaining here and there, and then try to explain you something which I find it very important for you to know. But otherwise, later on you can read the slide yourself now, and then if you have any doubt, you can always ask. Even while discussing today, also you can ask if you have any doubt, and afterwards also you can ask. All right. So as we mentioned yesterday, now it has got all the physical processes parameterized in it, starting from radiation, the surface processes parameterization, land surface processes, then planetary boundary layer, the cumulus convection or cumulus parameterization, cloud microphysics, and all of them also are allowed to interact with each other in the model. The model atmosphere is almost like a real atmosphere, although it is not perfectly real, but we try to mimic it, try to make it as much as possible real. So each of these physical processes also interact with each other, okay, as it occurs in the nature. We shall discuss briefly one by one. Okay, starting with the radiation. Okay, as you know, we have discussed earlier. Through this radiation parameterization, we try to compute the tendency of the temperature profile in the vertical, and also we try to compute the surface radiative fluxes. Okay, these are the major two aims of the radiation parameterization. Okay, how we do that we shall discuss quickly. Now this is a familiar diagram. We have seen this diagram earlier, right? And it illustrates all sorts of physical processes. I'm going to skip this diagram. Okay, as you know, the radiation has two parts. One is the long wave radiation, another is the short wave radiation. Okay, and in the WRF model, this radiation part, the long wave radiation part, is controlled by this parameter RA LW underscore physics. RA stands for radiation, LW for long wave, and physics for the physics option. Okay, so this parameter controls the type of long wave radiation parameterization that you want to use in the model. Okay, and we shall see different options. What are the options available for this? Now, this long wave radiation parameterization computes clear sky and cloudy sky, upward and downward radiation fluxes. Okay, that is one of the purposes of the long wave radiation parameterization scheme. It considers IR, infrared emission from layers of the atmosphere, different layers of the atmosphere, surface emissivity based on land type. Okay, because emissivity, as you know, will depend upon the type of land surface, whether it is vegetated or bare land or covered by snow or sandy and etc. Okay, so surface emissivity is based on the land type. Flux divergence leads to cooling in a layer. Okay, downward flux at surface is important in land energy budget. Okay, it computes the land energy budget where downward flux of radiation is very important. The IR radiation generally leads to cooling in clear sky, approximately 2 Kelvin per day. Okay. Stronger cooling at cloud tops and warming at cloud base. So all these things are considered in the long wave radiation parameterization scheme of the WRF model. Now these are the list of the options that is available to you. Okay, like you can choose any option, option 1 or 3 or 4, 5, 7, 14, 31, 99. Okay, and each of the options indicate, say for example, to choose option 1, that indicates RRTM radiation scheme, rapid radiative transfer model. Okay, was developed by Mlower et al. 1997, published in JGR, Journal of Geological Research. Okay, and this scheme was added in the WRF model in 2000, year 2000. Then if you choose the option 3, that means you are selecting CAM option for the long wave radiation scheme. CAM is the community atmospheric model developed at NCAR and generally used for the climate simulation. This scheme was proposed by Collins et al., published in 2004 in NCAR Technical Note, and was incorporated in the WRF model in 2006. And if you choose option 4, then it is RRTMG, slightly modified version of RRTM. Okay, it was modified by Iacono et al. 2008, published in JGR, Journal of Geological Research. Okay, it was implemented in WRF model in 2009, and so on, each of them. This is the new Goddard scheme. Goddard is the Goddard Space Flight Center of NASA. So this is a NASA scheme of radiation parameterization of long wave. Okay, and that is option 7. If you choose the option 7, that means you are choosing the no, sorry, this is 5. By choosing the option 5, that means you are choosing the NASA's Goddard scheme, and this was developed by Chow and Soras. Okay, and it is discussed in this NASA technical report, implemented in the WRF model in 2011. Then there is UCLA scheme, then there is RRTM-G, again another modification of RRTM, published by Baek et al. Okay, Journal of Applied Mythology, implemented in WRF model in 2018. Then Health and Swaraj scheme and GFDL scheme. If you choose the option 99, that means you are choosing the GFDL scheme, which was developed by Fels and Swarajkov, 1981, and implemented in the model 2004. So what you see from this list is that many scientists they worked on the radiation parameterization, and as and when they published the paper and developed the scheme, then it was again also tested in the WRF model, and accordingly an option was provided to use for the general public. You can choose any option for your radiation parameterization in the WRF model. Now questions arise that which is the best option? Okay, which is the best option? Which should we use? That is a very difficult thing to answer, because that you have to test by numerical sensitivity experiments. You have to test that which one works good for you, because although the thing is, if the radiation parameterization scheme was perfect, then that scheme should have worked perfectly anywhere on the Earth's surface, on the globe. But unfortunately, because no scheme is perfect, therefore no scheme works perfectly everywhere, right? And that's why people start improving it and adding new features into it, adding new schemes to interact with the cloud and aerosols and surface, etc. Okay, so these things are introduced in the newer schemes. All right, but it depends on which one works good for you. That is up to you to select. It doesn't matter that you must select the latest one. Say 2018 is the latest one here in this list. So it's not necessary that 2018 will work best for you. You have to test that whether it is really good, working good for you or not. And also, the later schemes are also expensive in the sense that it takes a lot of computational time. So you should have a good computer also if you want to use these schemes, the latest schemes. Okay, so that you have to decide that which one scheme you should select. Okay, am I audible?
Yes, sir.
Yes, sir.
Yes, sir.
Okay,
Yes, sir.
very good. Yeah, I'll have to check in between so that I should not get disconnected without my knowledge. Then what are the consequences? Okay, if you choose different options, 1, 3, 4, for different scheme, then what are the things that you are going to get? from there. Like you choose RRTM option 1, which is uh, available in the ARW model as well as NMM model. In both versions of the WRF, ARW and NMM, both the things it is available, RRTM option. Okay, and generally, it is very important for the chemistry because the gases, they interact with the radiation. Because you know that there are absorption bands in the radiation spectrum. Some gases absorbs very highly in certain wavelength. Some gases act as a window to certain wavelength. So chemistry option, core plus chemistry. Okay, so it is available in the ARW and NMM. Then if you choose this RRTM, that means you will have also the facility to interact with cloud microphysics species. Now your radiation scheme, the long radiation scheme will interact with the cloud water QC, rain water QR, cloud ice QI, snow and grapple. Okay, so RRTM scheme will interact with all these cloud species. You choose this option. Okay, for the cloud fraction, it only has either yes or no. If it is 1, that means you are allowing the cloud fraction to form. No, that means 0. And the greenhouse gases, whether the greenhouse gases are allowed to vary or they are fixed. So in this scheme, it is constant or is fixed, like it is used from the climatology, the yearly value of the greenhouse gases. Okay, so this is the thing. You choose this option for RRTM, then these are the things you are going to get. Similarly, if you choose the option 3 for CAM, the community atmospheric radiation, which is available only in the ARW model, then you are going to interact with the cloud water, cloud ice, and snow. And then in this case, for the cloud fraction, you are going to have maximum random overlap. You have studied this, right? For the cloud fraction, how the cloud fractions are treated now for the radiation, right? What are the 2 ways the cloud fraction, the cloud amount is treated? Can you remember?
So maximum overlap and random overlap.
Very good. And also mix one. Mix, that means maximum random both. Right. So it allows for this maximum random overlap. And in this case also, oh sorry, yes. In this case also, the greenhouse gases uh, is fixed. Okay, annually. Then similarly for other options, you can read for yourself because I'm going to skip many things. And once I have explained this thing, that means these things also are clear to you, I hope, because otherwise it will take too much time to explain or talk about everything. Okay. Then about the clear sky, IR active gases, the water vapor. Okay, the water vapor is obtained from the model itself because it is a prognostic variable, right? A specific humidity, del Q by del T, is available in the model. Okay, so that is allowed to interact with radiation. Carbon dioxide, well mixed, specified constant in whole atmosphere, and CAM has yearly value, as we mentioned. For CAM, RRTM and this scheme and RRTM-G and greenhouse gases input file can update carbon dioxide, N2O and CH4, methane and nitrous oxide. Okay. Then ozone, the schemes have own climatology. Okay. CAM has monthly journal pressure level data and RRTM has this as an option. Others use single profile. Goddard has 5 profiles to choose from. They're using the NASA scheme, option number 5. What was that option number 5? I guess you can check back. Then it can use 5 profiles of the ozone. And this diagram illustrates the absorption bands, the radiation. Left side is for the short wave, right side is for long wave, and they are the different gases. Okay, water vapor, carbon dioxide, oxygen, ozone, methane, nitrous oxide, relay scattering, etc., etc. So all these things that you have already studied earlier, they are incorporated in the WRF model. Okay, I'm not going to explain now these things in further in detail. Then, what the spectral bands? The schemes divide IR spectrum into bands dominated by different absorption gases. Typically, 8 to 16 bands are used. The computations use lookup tables for each band. Okay, there are certain pre-stored values which we don't have to compute every time step. Okay, so they are stored in the lookup tables for each band. Tables were generated from results of line-by-line calculations. Okay, LBL line-by-line calculations of the RTM models, the radiative transfer model. Okay, so they are fixed things, and so they are stored in the table so that the model doesn't have to compute it every time we are running. Otherwise, it will take further more time because computing this radiative transfer model is quite a complex thing. Right? So since they are fixed, they are not going to change, so they are stored in the lookup table. Then about the clouds, all schemes interact with resolved model cloud fields, allowing for ice and water clouds and precipitation species. Some microphysics options pass own particle sizes to RRTMG, okay, radiation, and it depends on what microphysics options you have chosen. Because all the microphysics we shall discuss later. What are the options available for cloud microphysics in the WRF model? And as you know that all the cloud microphysics schemes do not have all water species, in the sense that every scheme doesn't have cloud, ice, snow, grapple, hail, water vapor, liquid water, rainwater, everything. So it depends on which scheme you have chosen, right? And accordingly, only for that scheme the radiation scheme will work, right? Because if you choose a radiation scheme which expects different kind of cloud microphysics options or parameters, which your cloud microphysics parameterization does not provide, then it will fail. It will not work. Okay, you'll get error in the model. Okay, it will stop. So you have to choose the options carefully between cloud microphysics and the radiation parameterization, so that whatever your radiation scheme expects from the clouds, those should be available from the cloud microphysics scheme. Okay, and that's true for many other parameters also. Now, whether it is land surface process, or the convection and the cloud microphysics, because certain things are dependent on each other. Like if you choose one scheme, then you have to choose the other scheme compulsorily. Now, from suppose if you choose one scheme from the uh, land surface process parameterization, let us say plane and geo scheme, we shall discuss about it shortly. If you choose a plane and geo scheme for the land surface processes, then you must choose a related PBL option, because whatever input is required for the plane and geo scheme of the land surface processes, that must be provided by that PBL option. Otherwise, it will fail. It will abort. Okay. So they are dependent upon each other like that. Clouds strongly affect IR at all wavelengths, considered gray bodies, and are almost opaque to it. Okay. Then about the cloud fraction for microphysics cloud, there are three options like how to compute the cloud fraction. If you choose option 1, iCloud1 is controlled by this parameter iCloud. If you choose option 1, that means you are computing the cloud fraction based on Zhu and Rendell's method. Okay, if you are choosing the option 2, that means a simple 1 and 0 method. If you are choosing the option 3, that means it is using the Thomson's scheme, and that is available only in version 3.7 onwards. Further improved in 3.8. So all the version of the model which are after 3.8, this option is available. And cloud fraction for unresolved convective clouds. Okay. Unresolved convective clouds, and that will depend upon what is the resolution of the model. Because if your model is coarse resolution, that means it will not be able to resolve some of the convective clouds, and in that case, now the cloud fraction you cannot get from there. So only for that purpose, this is option available, and in that case you can set CU rad feedback equal to true. Okay, then it will allow for the cloud fraction for the unresolved convective cloud. Now it only works for GF. This is one of the convection scheme, GF. Okay, G3 this is also another convection scheme. G3, GT another convection scheme. So there are different convection schemes. KF. So this option CU rad feedback equal to true will work only if you are choosing one of these cumulus parameterization schemes. If you are not choosing the convection scheme among any of these three, then this option will not work. Okay, it will fail. JDM is another convection parameterization scheme. It separately provides the cloud fraction to radiation. Okay, it computes the cloud fraction in that scheme itself. Further, the overlap assumptions needed with multiple layers of varying fraction, like random overlap, maximum overlap, clouds is strict as much as possible, maximum random overlap, maximum for neighboring cloudy layers, random for layers separated by clear layer, and different WRF schemes may use different cloud overlapping assumptions. For example, RRTMG can use maximum random overlap. Okay, so it depends upon which scheme we are going to choose. So that was about the long wave radiation parameterization schemes available in the WRF model. Now, for the short wave radiation parameterization scheme, this is the option which controls it. RA_SW stands for short wave underscore physics. So this option will allow you to choose different schemes available for short wave radiation parameterization schemes. Now, in this scheme, it computes the clear sky and cloudy sky solar fluctuation. Okay, it includes annual and diurnal solar cycles. Most schemes consider downward and upward reflected fluxes. Dudya's scheme only has downward fluxes, it doesn't have upward fluxes, but other schemes have both downward and upward fluxes. It primarily a warming effect in the clear sky. I mean, the short wave radiation produces primarily a warming effect in the clear sky. The important component of the surface energy balance. Okay, this short wave radiation parameterization. They are the options available for short wave parameterization. They are the options 1, 2, 3, 4, 5, 7, etc., etc. And they are the schemes. If you are choosing option 1, that means you are using the Dudya scheme, which was published in Journal of Atmospheric Sciences in 1989, okay, and added to the WRF model in 2000. Similarly, the Goddard, that is NASA's scheme, you are choosing option 2 for short wave, that means you are using the NASA scheme developed by Chow and Swaraj. Okay, then CAM is for option 3, and so on. Now you can read yourself all these things. Now up to option number 99, which is for the GFDL. So I'm going to skip these things. Now, depending upon which option you are choosing, these are the things you are doing in the model. Okay, that also you can just read yourself these slides. And Dudya's scheme is available in both ARW and NMM. Okay, plus in the chemistry, WRM also. Okay, and if you are choosing this scheme, that means you are using all these cloud microphysical parameters. QC, QR, QI, snow, grapple, etc. Okay, it doesn't have any ozone. Whereas if you are using the GSFC, that is the Goddard Space Flight Center, okay, NASA scheme, which is available in ARW as well as the CAM, then you are only using QC and QI. Okay, you are not using other species. That is a simple cloud microphysics scheme. It has either cloud water or ice. Only two types, right? And in that case, in this case, I got profiles of ozone also available. For CAM, which is available only for ARW, there are 3 cloud microphysics parameters which are available to interact with the radiation short wave. Okay, and so on. You can just read all these things yourself, this table, and then decide that which scheme you want to select for the short wave radiation parameterization. The clear sky and aerosols are the main gas effect in troposphere is water vapor absorption. Carbon dioxide is a minor effect. Okay, so water vapor is the main gas which has a main impact on the radiation. Aerosols would be needed for additional scattering. WRF chemistry interacts with Goddard and RRTM short wave. Okay, Dudya scheme has tunable scattering. Okay, so whenever there is a tuning parameter, tuning factor, that means physics is not well understood, and so just a control is made available to improve your result or tune your result to make the impact of that scattering or that process. RRTMG has climatological aerosol input. So if you are using the RRTMG, that means you are using the climatological distribution of aerosols. And there are options for that available for that. Aerosol option 1, that means You are using the global monthly climatology of aerosol. If you are using the option 2, that means you have to specify the aerosols yourself, the aerosol optical depth map, and that you have to get from the satellite data. Okay, so all the provisions are available, whether you want to use the satellite data yourself or you want to use the climatological data globally, according to eventually your option. If you're using the option 3, that means the Thomson microphysics nuclei. That means in this case, this option 3 will work only when you are choosing the cloud microphysics parameterization scheme based on Thomson, and in which case now it computes the condensation nuclei. It has got the options for the condensation nuclei that is available only from version 3.8 onwards in the WRF model. Okay. Then ozone. Now, ozone heating maintains warm stratosphere. Okay, it warms the stratosphere because of the absorption. It is important for model tops above 20 kilometer, 50 millibar. Okay, if your model top is above 20 kilometer, that means this is very important to have ozone, proper ozone in your model. Usually specified from profiles and with long options. The ODI scheme has no ozone effect, as we mentioned earlier. CAM, RRTMG have zonal climatology, that means it is available or it is fixed zonally on a given latitude. The distribution of ozone is same everywhere. Okay, zonal climatology. CAM, RRTMG, and Goddard can also handle trace gases, mainly nitrogen oxide, nitrous oxide, and methane. Okay, so these are the options for the GHGs. Then spectral bands. Many schemes use multiple spectral bands. As with the long wave, bands are ranges of wavelengths usually dominated by different gases. Lookup tables, as I mentioned earlier, lookup tables are available for that, in which pre-computed fluxes from the RRTM are stored for utilization, and you don't have to compute those things again. You just use the lookup table. Clouds and cloud fraction, similar considerations to long wave, interacts with model resolved clouds and in some cases cumulus scheme, fraction and overlap assumptions, cloud albedo reflection, surface albedo reflection based on land surface type and slope out. Slope effect, okay, in the mountainous region, because of this slope of the topography, the way the radiation is absorbed at the surface can be slightly different from that of the flat surface. Okay, and so that effect is taken care of. And there are all the recent additions, people, as you know, they keep improving the schemes, and so they add new and new features. Earlier this feature was not available, now it is available. So this is available for all sort of options now. Represents effects of the slope on surface solar flux, accounting for diffuse and direct effects. Two levels of detail, namely options, slope rad. Okay, if you choose this, then it activates slope effects, may be useful for complex topography and grid length, which is less than 2 kilometer resolution. Okay, so that is also important. Unless your grid resolution is less than 2 kilometers, there is no meaning in activating this slope radius. Topography shading. Okay, shading of neighboring grids by mountains. See how people have tried to consider minute things in the model as it happens in the reality. Suppose a mountain is there which is shading the neighboring grid points which has no mountains, then it will have an effect on the radiation. Okay, and so that is taken care of by this topo shading. May be useful for grid spacing less than 1 kilometer. Again, further, unless your resolution is less than 1 kilometer, this will have no meaningful effect. Okay, use this parameter option only when your resolution is less than 1 kilometer. And in that case, it will take care of the shading effect of the topography at the neighboring grid points. Then time interval, RADT. At what interval you should calculate the radiation scheme or call the radiation scheme in the model. Okay, the radiation time step is recommended. It is recommended that you should carefully choose, because calculation of radiation flux rate is very expensive, and if you choose every time to calculate, then it will be too much of a computational time requirement. Okay, and also that it is not necessary, especially for example for this long wave. There is no need to calculate the long wave fluxes during the night time, because there is no long wave fluxes during the short wave fluxes during the night time, because there is no solar radiation. So on the global model, wherever there is a night, you don't have to invoke the short wave. Okay, you only have to calculate the long wave. And also, since you know that model time step can be in terms of seconds, a few seconds, depending on the resolution. So if your time step is 5 seconds, let us say, or 10 seconds, in 10 seconds, hardly any significant changes will occur because of the radiation fluxes. So you don't have to calculate the radiation fluxes every 5 seconds, that is every model time step. And there is an option available for that. That is through RADT. You can control at what interval you would like to call the radiation option. Earlier, in NCR of the model, it used to be 3 hours for the short wave, and I think for long wave it was 1 hour or something like that. But now for WRF model, choose RADT is equal to 1 minute. That means it depends on what is your grid resolution, and some kind of a hint is given, like per kilometer grid size, you should call the radiation scheme every minutes. So if your grid size is 10 kilometers, that means you should call the radiation scheme every 10 minutes. Okay, you don't have to call the radiation scheme, even if your time step is say 5 seconds or 10 seconds. Every time step you don't have to call the radiation scheme. Okay, you can call or calculate the radiation fluxes once in 10 minutes only if your grid distance, grid length is 10 kilometers. So it's approximate a hint is given for that. Each domain can have its own value, because each domain will have a different resolution. So depending upon the resolution of the domain, you can specify the value of RADT. Okay, coarser resolution of the domain will have larger RADT. Final resolution will have lesser RADT, shorter RADT. But recommended using same value of all domains. But for the experience of the computational problems, it is recommended that it's better to use the same RADT for all the nested domains. Okay, whether it's inner domain or outer domain. The surface short wave fluxes is controlled by this parameter SWINT option equal to 1. Choose option 1, that means you are allowing for surface short wave fluxes. It provides a smooth surface downward flux over time, interpolates between radiation steps using cosine zenith angle and clearness index. This also allows smoother variation of ground variables and fluxes. It eliminates steps in time series. It allows for diffuse, direct, and direct normal short wave components. Now, these are the outputs. These are the output variable names, and aerosols, effects, diffuse, direct, ratio. Okay, these things are also accounted for in the surface short wave fluxes. So that was about the radiation parameterization schemes available in the WRF model. Now, what are the schemes available and what are the functions available? Okay, so after this radiation, already we have spent how much time? 45 minutes almost. Okay, so I've got another 15 minutes. You have a class at 3:30, right?
Yes, sir.
Yeah, so we will stop in after 15 minutes. So try to finish as much as possible, because a lot of slides are there for the physics option. So next is the surface scheme. Now the surface scheme, the surface layer of atmosphere, calculate the diagnostics of the surface layer of the atmosphere. That means exchange transfer coefficients, latent heat fluxes, the sensible heat fluxes, and also it interacts with the land surface process scheme. Don't confuse with the surface scheme versus the land surface process scheme. Surface scheme is for the surface layer of the atmosphere, whereas land surface is for the land surface, type of land, soil, characteristic, vegetation, etc. So this scheme interfaces or interacts both with the land surface scheme as well as the surface layer and the layer above it, that is PVL. Okay, and actually surface layer itself is a part of the PVL. Right. So the atmospheric surface layer, as you know, it interacts with the land surface model, and it also interacts with the PBL model. The land surface model also interacts directly with the PBL model. Okay, so between the atmospheric surface layer and the land surface model, the exchange coefficients for heat, moisture, etc. are calculated. Then between this and this, the frictional stress and water surface fluxes of heat and moisture are calculated. And similarly, between this and this, land surface fluxes of heat and moisture are calculated, which directly influences the PBL. Okay, these are the objectives or tasks for the land surface, for the surface layer parameterization schemes in the WRF model. And there are surface fluxes given. I'm going to skip this slide because these formulas, etc., you have studied earlier in the theory. Okay, heat fluxes for heat, fluxes for moisture, fluxes for momentum, heat, moisture, momentum are computed. Okay, in the model using these formulas. Right? I'm going to skip these things. Then roughness length, another important parameter. The roughness lengths are a measure of the initial length scale of surface eddies. Okay, and generally differ for velocity and scalars. You have studied the roughness length, right? The definition of the roughness length. You remember that?
Yes, sir.
Okay, good. So these things you should remember because these things may come as short questions, right? Short notes, etc. Sometimes even multiple choice options. The roughness length depends on land use type, as you can very well imagine. Some schemes use smaller roughness length for heat than for the momentum. Okay. For water points, roughness length is a function of the surface wind speed because the roughness length is proportional to both wind speed as well as the type of the surface. Okay. So these things are taken care of. The exchange coefficients are also computed as part of the surface layer parameterization scheme. And we are the formula for that. I'm going to skip these things. So study these things in the theory part earlier. Then this is the name of the parameter which controls the surface layer physics. SF underscore SFC layer underscore physics. And depending upon which option you are choosing, it uses similarity theory to determine exchange coefficients and diagnostics of the 2-meter temperature of the air and specific humidity and 10-meter wind. Okay, so to compute the exchange coefficients based upon this similarity theory, it uses the 2-meter temperature, specific humidity, and 10-meter wind. It provides exchange coefficient to land surface models, provides frictional velocity to PBL. Scheme provides surface fluxes of water vapor points, our water point, that means our ocean surface, our river, our lake, etc. The schemes have variations in stability functions, roughness length, etc. These are the functions, okay, or responsibility of the surface layer parameterization scheme in the WRF model. Now, for certain applications like we are running the WRF for hurricane, cyclone, now forecasting, they call WRF, HWRF, hurricane WRF. Okay, so in that case, some additional features are available because in that case, especially you need to have a better analysis of the ocean parameters. Okay, you should better resolve the ocean parameters like mixed layer depth, etc., ocean mixed layer depth, etc. So in that case, you have to choose the option SF Ocean Physics 1. Then we'll take care of the ocean mixed layer. And it considers a one-dimensional slab ocean mixed layer. Specified initial depth includes wind-driven ocean mixing for SST cooling feedback. Okay, then there is a 3D PWP ocean developed by Price et al. If you choose the option 2, okay, if you're choosing the option 1, that means you are using the ocean mixed layer model. If you're choosing the option 2, that means you are using the 3D PWP model as discussed in the Price et al. paper, which is a 3-dimensional multi-layer ocean model. It has got the salinity effect, okay, and I got the fixed depth in the vertical. Alternative surface layer options for high wind ocean surfaces are also available. And you can choose ISFTC flux equal to either 1 or 2 if you want to choose this option for strong wind conditions over the ocean surface. So use this option SFC lay surface layer physics equal to 1. Now, if you want to use these options, modifies Charnock relation to give less surface friction at high winds and low drag coefficient, modifies surface enthalpy, CK, heat, moisture, either with constant Z0, that is surface length, okay, roughness length, with this option, and depending on based on this Garat formulation, that is option number 2. Okay, this one. So these are the options available which you can read yourself. Then the options available for considering the sea ice. Suppose if your domain is covering area where there is a sea ice, like Antarctica, etc., very high latitude, etc., then you can choose this option by specifying fractional sea ice equal to 1. With input sea ice fraction data can partition land water fluxes with a grid box. It can be used with nearly all surface layer schemes. Okay, so if you are using for the Indian domain, Indian region, then this is meaningless because there is no sea ice in our region. The WRF land surface model options. Land surface model, we have already studied in the class, in the theory class, right? What is the time? Do you remember the land surface processes schemes that you have studied? Yes or no? Have you studied or not? We have discussed in the class or no? Am I audible or not?
Yes, sir.
Yes, sir.
Okay. So if you recall, we had studied the land surface processes parameterization scheme during the theory class. Okay. And here are the options available for that scheme in the WRF model. Okay. Controlled by this name list parameter, SF surface physics. And what are the things available? One option is simple 5-layer soil model. Other is NOAA LSM, NOAA MP, RUC, rapid update cycle, land surface model, Plemenju, land surface model, CLM4, SIB, simple biosphere model, land surface model, and so many things are there. And various scientists have studied or developed various schemes, different schemes, claiming that this scheme improves upon the older scheme, and all those schemes are available because, as I said, that it is not necessary that whatever work for that person in his area of interest will work same in your area of interest also. So all these options are still made available, even though some of them are quite old. So as it indicates, as this name indicates, you choose this option. That means your land surface has about 5 layers in the soil below the earth surface. There is no vegetation or snow cover prediction scheme available in this model. Just thermal diffusion in soil layers. And these things are available in some of these schemes, which are actually sophisticated vegetation model and snow cover prediction model. Okay. So these are the things available. And this is illustration for the land surface processes. This diagram we have discussed in the theory class, if you recall. Okay, so I'm going to skip this slide. And these are the land surface processes. This also we had discussed in the theory class, if you remember. Okay, like when there is a rainfall, then the precipitation can be intercepted by the trees, vegetation, wherever there are trees and vegetation on the grid point, and if the grid point is bare soil, there is no vegetation, then it will enter the soil. Okay. Then from the trees, transpiration will occur, canopy water evaporation will occur. Okay, canopy water drift will occur, and then there is a root zone for the tree. It depends upon how many layers you have got under the soil. Accordingly, this will be treated. Okay, internal soil moisture flux will be calculated. Uptake water, root water will be calculated by the land surface model scheme. Then there will be evaporation from the ground that will be calculated, direct soil evaporation. Then evaporation from the open water like lake, ocean, etc. will be calculated. Then if there is a snow surface, snow covered land, then deposition, sublimation to or from snowpack will be calculated. Okay, and if there are grasses and bushes, then accordingly the calculation will be also changed. Deposition, evaporation, etc. from the surface will be taken into account. The turbulent heat flux to and from the soil, slope, plant, etc., canopy, etc., will be taken care of. So these are the various functions of the land surface model processes, parameterization schemes. Okay, it is driven by surface energy and water fluxes. It predicts soil temperature and soil moisture in layers 4 for NOAA and NOAA MP, 9 for RUC, the 9 layers, 2 for Plemenju and 3 for SSIB. Different schemes has different soil layers, 10 for the CLM4, 10 layers for the CLM4. It predicts snow water equivalent on ground, maybe in layers, and for these schemes, NOAA MP, RUCs, etc. Many predict canopy moisture only. That is in the NOAA scheme and in the RUC scheme, only the canopy moisture is predicted. Or temperature only is predicted in the SSIB scheme, or both in the NOAA MP and CLM4. Okay. So these are the options available for your land surface models. 1, 2, 3, 4, 5, 7, and 8. That means you are choosing option number 1 for SF surface physics. That means you are using the 5-layer slab model for the land surface process parameterization. And details are given in the Studia 1996 reference. You are choosing option number 2. That means you are using the NOAA scheme. Okay, this is a reference for that. If you are choosing option 3, that means RUC, rapid update cycle scheme. Okay, scheme option number 4, that means NOAA MP. Option number 5, claim 4. 7, claim NGO scheme. And 8, simple biosphere. Okay, so these are the different options available for choosing different land surface process parameterization schemes in the model. And depending upon which option you are choosing, accordingly you are treating the soil temperature, snow, etc., soil temperature accordingly, because the number of layers in the soil, not the soil, are different in different models, and it's given here. Okay, you can read for yourself. 5-layer model, obviously I got 5 soil layers. Okay, NOAA I got 4 soil layers. Maximum is available in CLM4, 10 layers are available for the CLM4, and some of them treat only the temperature, like 5-layer model, it doesn't have no options for the moisture and snow, whereas some other have options for all those things, like in NOAA scheme, in Rook scheme, and all other schemes, everything is treated, computed, soil temperature, soil moisture, and snow layer. Vegetation and soil processes including evapotranspiration, root zone, and leaf effects. Vegetation fraction varies seasonally. Okay, so that is allowed. Vegetation fraction is allowed to vary seasonally, because in some season some crops will be there in the field, like paddy will be there in some season, wheat will be there in some other season, and etc. So those seasonal variation of the vegetation fraction is allowed depending upon which scheme you are going to choose. Okay, it considers vegetation categories. That is, as I mentioned earlier during your theory class, that there are different types of vegetations characterized or classified. What depends on which scheme you are choosing. Or 20 to 25, 30 types of vegetations are classified. And that is whether it is a cropland or it is a forest type, which forest type, etc. etc. It considers soil category, that is whether it is sandy, clay, etc. for drainage and thermal conductivity. Snow cover, accordingly it treats the snow cover in different ways in different. I'm rushing because I'm almost I've crossed the time. So I want to finish this land space scheme before you go. Then some options are available for including the urban effects. Like in this case, there are separate modules available for urban model. Okay, and in that case, you have to choose or invoke that option by this name, surface urban physics with NOAA, and this is available only for NOAA land surface model. Okay, and then in that case, it will compute the effects of the urban canopy, building environment parameterization, etc., building energy model, and so on. Okay, I'm going to skip these things. Land surface model tables, they are the lookup tables I was mentioning you earlier, and they are available in the WRF model by different names for the vegetation parameterization, by veg param table, MP table for the NOAA MP, soil parameterization, etc., land use category, urban parameterization, etc. So they are available in the WRF model. Okay. Now, it's very important. I want to finish, but you are almost is the time, because initializing the land surface model is very important, because the soil moisture and soil temperature can vary from place to place, and if you have the available data available for soil moisture, which is nowadays normally available from the satellite, also from the ground observation, so you'd like to assimilate those observations, just like you do the data assimilation from the upper air. Similarly, you can do the assimilation of soil moisture and soil temperature, right? And for that, options are available, and that is called initializing the soil moisture land surface model, and that is available if you are choosing the NOAA option or root LSM. In this case, you can initialize soil temperature, soil moisture, and slow liquid equivalent, and assimilate them also in the model now based upon the observation, real-time observations. These are in the grid files, but are not from the observation. Okay, they come from offline models. Actually, the thing is that sometimes, unlike in the atmospheric data simulation, which is generally done at 6 hourly or 3 hourly or 1 hourly, depending on your interest, whether it's a convective scale or large scale, etc. The land surface initialization is done not every hourly or 3 hourly, but maybe once in a day or so. Okay, because soil temperature or soil moisture, as you go deeper and deeper, those things don't change much, as you know. So you don't necessarily to assimilate the soil temperature moisture every hour or 3 hourly or so. Okay, so these are the ways it is done in different models. I'm just going to skip because I'm already crossing the time. Initialization of the soil moisture. Many good papers are available to read about the impact of initializing the soil moisture on the prediction of the, say, for example, thunderstorms, etc. If you are initializing properly the soil temperature and soil moisture, just like you have a proper initial condition for the model, then you get a good forecast. Similarly, if you have proper boundary conditions at the surface of the soil moisture and soil temperature, you will have a better evolution of the convection, okay, and other processes, and better prediction of the weather systems. Subgrid mosaic, okay, these things are available in NOAA and RUC, and also in the Clemengeau. Okay, default is one dominant vegetation and one soil type per grid cell, but you can have a mosaic of different types of vegetation and soil types. Then there is an option available for SST update. If you have SST data available to you every day, then you can use this option. If you have not, then just use an option in which it just uses the SST climatology rather than using the SST every day. And especially if you have a couple model like ocean model, then you can get SST every time step also, because the ocean model is providing you the SST in that case, right? So it depends, especially if you are using the WRF, like hurricane WRF or cyclone prediction, then this is very important. Okay, and also for the long integration, seasonal integration is very important. Okay, but for short range, this may not be so much important. Okay, SST update. I'm going to skip these things. Regional climate option. Again, but if you are going to make a climate scale simulation, then these different options are available, and you can read this slide later on yourself. Self-explanatory. Lake model. If your domain has a lake, if your domain is so big that it has a lake also within your domain, then you can compute the effect of the lake by specifying certain options like SF lake physics 1. If you are specified, that will it will compute the effect of the lake, which may be available in your region or in your domain. Okay, I'm going to skip these things. Read yourself. Then there is WRF hydro, especially we are going to use it for hydrological applications. Okay, stream flow prediction, runoff prediction, floods, etc. Then you can use this WRF hydro. All right, so we completed the land surface processing scheme as well as the surface layer parameterization schemes. Are you all there, or how you have managed? Are you?
Yes, sir, we are here.
Don't very good. So everybody is there. Yeah? This is 12 or 11 people, maybe 10 people, maybe. Yeah. So all right, we have already crossed the time limit, and so I'm going to stop my presentation. And tomorrow we shall see. Hopefully 11:30 class. Let us see, because new admission is yes.
Sir, I need to ask something about the research paper.
About what?
Research paper, sir.
अच्छा ठीक है तो ऐसा करें. Can we discuss it at 4:30, because now you have a class, right?
Yes, sir, but now are you free, sir? Because me and Anish are not having any presentation in this class.
I see, okay.
Yes.
So you two are free now. So okay, quickly we can discuss. Others can go and join the other classes.
Thank you, sir.
Yeah.
Thank you, sir.
So you and Anish can remain here. All right. And I'm going to stop the recording because there is no need to record this part.
Yes.
Stop recording. So Sayoni has got it today.